I think the error bars got smaller. The line was built.
Hi everyone, thanks for coming on such a nice day. We should all go outside. So we are kicking off our high energy seminar. Our first speaker is also the organizer of this seminar, Dr. Bogdan. And Akash was an undergraduate student at Altavas University in Budapest, Hungary. And he did his PhD in Max Planck Institute with professors Bogdanov and professors Samia. And he was there. He was studied hot gas around galaxies and also the origin of type 1 supernovae. And later he became a postdoc as an Einstein Fellow at the CFA. Then he joined the Chamber Calibration Group. And his research interests about hot gas around galaxies, clusters, and supermassive black holes and the connection between them. And today he's going to talk to us about the correlation between the mass of galaxy clusters and the supermassive black holes.
Okay, thank you. So for a long time I thought that if I'm organizing this seminar series that I don't have to give a talk. It has worked out for quite a long while, but apparently not forever. Anyway, so today I hope I will tell you something really nice and simple, but you can tell me after the talk. So today I'm going to tell you about the connection between the mass of supermassive black holes in the center of galaxy clusters residing in brightest cluster galaxies and brightest group galaxies, and the total mass, and I'm going to connect this with the total mass of the host galaxy clusters. So obviously I didn't do this work alone. So Lorenzo had me a lot with the data analysis, Marta voluntary, and Johan Dubois, they helped with the simulation part of this analysis, and we are still working on that. And Freddie Phipps, who is a Southampton student, and who is working with me and Lorenzo, and she's doing some follow-up work, and I'll show you some results later on that follow-up work. So this paper is published, has been just published a few weeks ago in AppJ, and if you want to read more, or if you want to read the proper captions for everything, for all the plots, then you can do that by reading this paper. I can turn this on. So, before we move to clusters and all kinds of fancy stuff, let me just tell you a few words about the basics and give you some introduction. So, since the advent of dynamical black hole mass measurements, which resulted in very accurate black hole masses, it has been discovered that the mass of the supermassive black holes in center of galaxies exhibits all kinds of correlations with various properties of their host galaxies. Most famous relations are, for example, with the stellar bulge mass and with the central stellar velocity dispersions. And all these correlations basically say that bigger mass black holes live in galaxies with bigger stellar bulge, and massive black holes live in galaxies which have high velocity dispersions. Okay, I'm not going to argue how tight this relation is. It's not particularly tight. It has like 0.4 Dex scatter, and these are actually only elliptical galaxies. But let's just agree that there is a correlation between the black hole mass, stellar bulge mass, and black hole mass velocity dispersions, and all kinds of other correlations exist out there. So the main point of this talk is not the existence of these correlations, but a subsample of these galaxies. If you look up here, you will see a bunch of green points. Okay, you see these green points here as well, and what you will note, and these green points are actually galaxies or black holes which are sitting in the brightest cluster galaxies. Okay, and what you will notice is that they are systematically over the best fit relations, best fit local relations, which suggest that the black holes residing in brightest cluster galaxies are overmassive relative to the scaling relations. So what does it mean? Something funky is going on there. It might raise the question whether or not they evolve differently than black holes, than your normal regular black holes, which are sitting in so-called satellite galaxies and not in the brightest cluster galaxies. So what's going on there? And of course, the question is whether the cluster and the large-scale potential of the clusters have anything to do with the evolution of these black holes sitting in the brightest cluster galaxies, or BCGs. Okay, from now on, I'm just mentioning that from now on I'm going to use BCG sometimes also for group galaxies. So anything which is sitting in a big, in the center of a big potential, I'm just going to call them BCG sometimes. Okay. So let me just illustrate the scales here and what I'm trying to talk about. So here on this upper image, you can see this is a simulated image from the Horizon AGN simulation, which comes from Marta Volonteri and Johan Dubois. You can see the dark matter distribution, and the underlying image shows the dark matter distribution, and the colors, they show the gas temperature. So of course, you have here the hot gas, and here in the intersection of filaments, you have the nice galaxy clusters. And if you zoom in, then this is just an optical image from also from the simulation. You see the bunch of galaxies, and here you have the scale bar is 20 megaparsecs, so it's huge. Then here, galaxy cluster size, so it's 2 megaparsecs, the scale bar. And if you do another factor of 4 zoom in, is like 500 kiloparsecs. So here you see the brightest cluster galaxy, also another galaxy. And in the center of this this galaxy, you have the supermassive black hole, which has a tiny, tiny scale. You see it's 10 to the minus 3 parsecs. Okay? So what I'm suggesting here is that actually the growth of the black holes might be to some extent regulated by processes which are happening on the scales of megaparsecs. So there is, I think, like 10 orders of magnitude difference here, if you think about it. It's pretty crazy. So let's see if this might make any sense. But before we do that, what could happen? So of course, I'm not the first one who realized that black holes in BCGs are overmassive. But so the idea is that there are different evolutionary processes acting to grow these black holes, and that's why they are so massive. So what could be this? Nobody really knows. Obviously, there are a couple of ideas which might have something to do with the fact that these black holes are sitting in the center of a huge potential. So there could be some direct gas flows onto the cluster center, which could, in fact, if they have low angular momentum gas secretion, then they could act as a process which grows the black holes quickly, but not so much the stellar mass of the galaxies. Also, mergers are very frequent in the centers of clusters because you have many galaxies there, so black holes could grow additionally. Or there could be some residual cold gas, which could, again, help to grow the supermassive black holes. Okay, so let's just explore the connection between the black hole mass and the total mass of the galaxy clusters. And that's what we want to see, if there's a correlation between these two quantities. So what do we need to explore the connection between the black hole mass and the M500 mass? Well, obviously you need the black hole mass, right? And what will be the other thing is the M500 mass. So in order to keep it nice, easy, and clean, we start with dynamical black hole mass measurements. So dynamical black hole mass measurements are good because they are very accurate. We don't use traces, we just use the literature data. So the advantage of dynamical black hole mass measurements is that it's accurate. But they are also difficult, which means that we can do them only out to a limited distance, like 100, 150 megaparsecs, given the typical black hole masses. And this limits our sample by a large factor. This means that overall, up until this review by Kermandi and Ho, we had like 88 black hole mass measurements, dynamical black hole mass measurements available. This might be a little bit more today, but that's a rough number. Okay, so we are still below 100. Out of these 88, only roughly like 36 of them reside in the center of groups and clusters. So this is our initial sample. As I said, we also need total masses of galaxy clusters, which I'm just going to use the M500 radius here. And I'm not even using the M500 radius. We could try to measure the M500 radius using X-rays, but measuring the M500 is a difficult thing. Why is it difficult? You could assume that the hot gas in the galaxy group or cluster is in hydrostatic equilibrium. The issue is that you need to measure density profile, which is fairly easy, and you need to do a temperature profile as well. Measuring temperature profiles is not so easy. It needs many counts, and you might not have those counts. For many of these clusters, we actually have relatively short observations, and some of the groups are fairly faint, which means that we can only extract a single temperature. Okay, so we can get around that problem by using the M500 KT relation, so the best fit single temperature of the cluster, because there's a tight correlation there. So many people, including Lorenzo in one of his earlier papers, has shown that there's a tight correlation between the M500 and the best fit gas temperature for galaxy clusters and galaxy groups. And it's basically the same relation or very similar relation both for clusters, which are here, mostly shown with red points, and for groups, which Lorenzo has compiled. So out of those 36 black holes with dynamical black hole mass measurements, we only have data for 22. A couple of them had to be excluded, and another couple of them were X-ray faint. These are really low mass black holes, so like 10 to the 7 solar mass black holes, and they are just not detected with XMM Newton. So we are left with a final sample for 17 galaxy groups and clusters. Okay, so this will be our sample that we are going to use. So black hole masses are given. We just take them from the literature. Stellar barge masses are also easy. We also can take them from the literature. M500, instead of M500, we just measure the KT. So we are building the black hole mass KT correlation here. Now, Lorenzo had me, or he actually used, he used all his skills to measure very proper gas temperatures. So how he did that, I'm just going to put some buzzwords up here. So he used fairly standard data analysis with XMM. So we filtered high background periods, excluded all the point sources. You're all familiar with this. And of course, we took care of the background very properly. One issue is that, as I mentioned, in order to do dynamical black hole mass measurements, you need the clusters and groups which are fairly close. Okay? This includes the Virgo cluster, for example. Virgo cluster is close. And you want to measure the gas temperature within the R500 radius. But of course, the XMM field of view is tiny compared to the R500 of many of the clusters and groups we have here, which means that we cover different fraction of groups and clusters. And sometimes it's only 9% that we cover, and in some cases we cover like 100% of the cluster. So I just show here two examples. Able 1836. Able 1836 is a galaxy cluster at 150 megaparsecs away, and we cover it entirely. So the red circle shows the R500 radius. The same is not true for Able 3565, where we only cover 40%. And you might wonder, okay, Ákos, what are you doing here? You're measuring the temperature at different radii. It's going to be all messed up when you try to compare, and then you will be biased, and you will introduce all kinds of effects. As a matter of fact, we have looked into this very carefully, and it turns out that we don't really. You can kind of ignore the axis here. These are temperatures measured in different radii for archival sample taken from Gabriel Pratt's paper, and this is for our paper. And the thing is that as long as the red points, which are the galaxy clusters in our paper, and this is like other galaxy clusters, as long as the red points are fairly close to the solid line, then we can say that the temperature is fairly insensitive to the extraction region. Okay? So this is why we are more or less confident that we are not making a huge mistake when some of the clusters, when we measure the gas temperature for some of the clusters only within 10%, and in some cases we measure it out to like 50, 60, whatever %. Okay? So now we trust I trust, Lorenzo trusts, I hope you also believe us. Now we have the gas temperatures, and we have the black hole masses. So why don't I show you just the relation? Okay, there you go. So this is the black hole mass gas temperature relation. So y-axis black hole mass, and this is the KT temperature. So we can measure also the correlation coefficients. I just show you here this Spearman correlation coefficient, which is 0.83. Pearson correlation coefficient is even better. That's 0.95, I think, or something like that. And you see, it's a fairly nice relation. That's the best fit relation. Okay? And you might be wondering how it compares with the, and here are the scatter values, okay, the X and Y scatter. And you might be wondering how it compares with the so famous stellar barge, the black hole mass barge mass relation. That's a famous one, right? That was one of the first relations after the Wells dispersion relation was discovered. So how does it compare? Like that, okay? It's a much poorer relation. You see, it has a Spearman correlation coefficient of 0.3. And then it has like, it's almost like a scatter relation. You actually see with numbers, scatter is huge. Let me just jump up a little bit between the two. Okay? So do you agree with me that this relation between the cluster temperature is tighter than this one? Yeah? Yeah? Kinda? Yeah? Okay. Numbers show that. So what does it tell? For a sample of 17, this is not the end of it, almost. So for a sample of 17 galaxy groups and clusters, we can say that the black holes in BCGs exhibit a tight relation with the total mass of the host group or cluster. Okay? And we can also say that the black hole mass KT relation, or the M500 traced through the gas temperature, is significantly tighter than the black hole mass Budge mass relation. So it suggests that the large-scale galaxy potential actually plays a role in growing the black holes in BCGs and in brightest group galaxies as well. Of course, I have simulations to compare our observations with, and our goal is obviously to find out what are the processes which aid the growth of black holes in brightest group and brightest cluster galaxies. So in order to do that, we used the Horizon AGN simulation, and the Horizon AGN simulation is a cosmological hydrodynamical simulation, and instead of just words, I just show you a video which you can all look at while I tell you a few words about this simulation. So the Horizon AGN simulation uses the adaptive mesh refinement called RAMSES, and it has all major physical processes that you need to produce a realistic galaxy population. It has feedback from stars and supernovae. It includes black hole formation, black hole accretion, and black hole feedback, so AGN feedback. And you will see some AGN feedback, some immediate, there you go, there are the AGN feedback realizations. And it includes prescriptions for background UV heating, gas cooling, star formation. So all in all, it has galaxies which are realistically looking. It has galaxy groups and galaxy clusters. As a matter of fact, it has 484 galaxy groups and clusters which are more massive than 5 times 10 to the 12 solar masses. Okay, so this gives us a first good step to compare our observations with the simulations. So I show you the nice results. All the gray points here, so this is black hole mass M500 and black hole mass M500. So the observed points, for the observed points, we just use the M500 KT relation to convert, to obtain the values. And for the gray points are coming from the simulations. So you see there's a fairly good agreement between the observations and the simulations. What you can immediately tell is that the simulations are much tighter, predict much tighter relations than we in fact observe, and this is especially true for the black hole mass Budge mass relation, which provides an extremely tight, like 0.2 deck scatter relation. Okay, so I'm not going to tell you much more about that. So this is still in progress, but all in all, the key point is that this provides a framework. So the simulation provides a good framework to probe the origin of the black hole mass and the M500 correlation. Okay, and we are still looking into it and hope that we will be able to better narrow down the process that actually, at least the processes that actually help growing these black holes in BCGs. Now, one of the issues is that here on this plot we have only 17 data points. It's not too many, right? 17 is not a huge number. What would you want to see? You would want to see this for a much larger sample. Okay, so this is where Freddie's work is coming in picture, who is doing some very good follow-up work. So we have two issues. One of them is that most of these objects, if you look at the mass range, are groups, and we only have a handful of clusters. So we need first more objects, more clusters, and more massive clusters. Okay? However, dynamical black hole mass measurements, as I mentioned, are very expensive. And you cannot do them out to some arbitrary large redshifts. You cannot measure a dynamically black hole mass of a 0.3 class or a 0.3 redshift 0.3 galaxy, right? So in order to avoid that issue, you must use some tracers, and you can use different tracers. And what I'm going to highlight here is that we are going to use the fundamental plane of black hole activity. So what is the fundamental plane? Just a reminder. So basically, it connects the radioluminosity and the X-ray luminosity and the black hole mass of black holes, of the supermassive black holes. And it appears, and I took this picture from Andrea Merloni's paper. It looks like a nice relation if you don't look at the numbers on the axis, But you might notice, if you look at the numbers, you might notice that it has actually 20 orders of magnitude on the y-axis and 15 orders of magnitude on the x-axis. So even tiny outliers here are easily 2 orders of magnitude outliers from the main relation. So whenever you look at this, look at values or black hole masses inferred from the fundamental plane, you have to be a little bit careful and treat them accordingly. So the scatter in this relation is like almost 1 dex. In any case, that's the best we can do for a larger sample. So Freddie is doing multiple approaches, but one of the approaches that she's doing is that she's using the fundamental plane of black hole activity for a sample of black holes. Especially, she's using 72 clusters and their BCGs, and the black hole mass inferred from that to do some follow-up work. So the black hole masses, the inferred black hole masses are given in this work. Marc Mesquier, who was a postdoc here, and now is working with Julie Larondo in Montreal. And Freddie is actually measuring the galaxy cluster temperatures using Chandra data. Okay? And she's essentially doing the same thing. She's measuring the cluster temperatures, and we are going to connect that with the black hole mass. So, without further ado, here is the result that Freddie got. And that's an initial result. So the final result will be presented by Freddie in May. Right, Jeremy? May, yes. And what you can see here is the black hole mass, again, and the gas temperature on the x-axis. And there are 2 sets of points. The blue points are from my paper and from the work I just presented here. And you see, so these are all the same points. And you see the best fit line is the same best fit line which I just showed you before. The red points are from Freddie's work, and the black hole masses are inferred from the fundamental plane. Okay? And you might not notice that, but there is a dashed line. And weirdly enough, this dashed red line is totally coincident with the blue line. Okay? And again, the blue line was obtained only for my data points, for the data points presented in my paper, and the red points are, or the red dashed line is a fit only to the red points. Okay? So there's a weird coincidence, like all the numbers are coincident, all the best fit numbers are coincident with to the second digit. So that's quite impressive. What is not so impressive is the scatter. If you look at this relation, the red points have huge scatter. So why is that? We are not entirely sure. Part of the reason, I believe, might be that this large scatter is in fact originating from the fundamental plane itself. Okay, so what might happen is that our input relation, which we use to infer the black hole mass, has large scatter, and that's what we see here again. Okay. So with that, I arrived to my conclusions. So a couple of conclusions. So the black hole mass of brightest group and cluster galaxies appears to correlate fairly tightly with the gas temperature, or M500, of the host group and clusters. It also appears that the black hole mass gas temperature relation is tighter than the black hole mass bulge mass relations. So what this suggests is that addition processes might help grow the black holes in BCGs, which processes are actually governed with the large scale potential. And we need follow-up work in order to extend the cluster sample, and we are performing follow-up work to understand what's going on in the simulations and to better narrow down what might be going on. So thank you very much. Oh, so many questions.
So if you go back a few slides, maybe 4, 5, or 6 slides, where you did a comparison of the simulation to the right there on the right. So one of the ways people test their simulations is to compare them to data. And so when you look at that, you say, gee, it didn't do such a good job. So does this imply that there's actually something wrong with the way the simulation, the way they grow the black hole and the stellar component?
I saw some simulation people here, so they probably can
put it up.
Yeah, they can better answer that. So the thing is that simulations are tuned to actually match these relations, match a couple of relations. I think this is one of them, correct, Oksana? Yeah. Yeah, but for example, illustrious. That's not for this. Okay. So some of them are, according to my conversation with Marta, so some of them are tuned to match these relations or some of the black hole mass galaxy relations. And that's like a common problem with simulations, is that they predict very tight relations.
So there's something more that needs to be added.
Yes, something more, yes, probably.
Because those observations are presumably pretty good.
Yeah? Yeah, so I would trust this, yes.
Okay.
This is really nice. So to what degree do you think that this relation reflects a real causal relationship? To what degree do you think that this is a reflection of the standard complaint of log mass plots? Everything's a straight line in log mass space because big things have more of everything.
Well, when you compare, when you actually compare, when you compare the tightness of these two relations, it tells me that this might be more important, at least for BCGs, than the classical picture is that black holes and BHs, they co-evolve and they grow together. Okay, that might be true to some extent in BCGs, but there is something more to that. Okay, so I'm not going to say what is causal and what is not. It's a dangerous game to play. But what it tells me is that clusters do play a role, and the processes which are governed by the large-scale potential do play a role here. That's what it tells me.
Ankush, just out of curiosity, you basically have, let's say, three variables in your correlation. There is the mass of black hole, I'm simplifying. There is the stellar mass, and there is the temperature, right? So you looked at the mass black hole versus temperature. That's what you do here. And you have the mass of black holes versus stellar mass. Have you looked at the stellar mass versus temperature?
Very good, thank you. I was looking for it. I was waiting this question. There you go. So, it's the situation is not that this relation, the barge mass, Katie, this is what you wanted to see, right? So this correlation is not driving everything. So it's not true that only because bigger clusters have bigger barges. So this is not driving anything.
Have you tried a partial Spearman rack just to get some numbers?
I think no. No is the answer. Haven't. Is it? Then maybe we did.
At least I calculated this. It's available.
I don't think it's in the paper, whatever. That's why I cited the paper on the first slide, see?
All right, so this is very nice work. I wonder about the statistical significance often of the basic claim these BCG black holes are ultramassive. I mean, it's not like they're way off.
The very first slide, you mean?
Yeah, the very first slide.
I mean, that's only a handful of objects. Yeah, when you look at it, that's only a handful of objects, of course, which are above. The difference is that there they only highlighted BCGs, whereas in this work we also included the brightest group galaxies. Okay, so that's why we have more objects here.
Yeah, so I wonder if there's like systematic errors, for example, at high masses, then whether that would take the effect away or not.
Well, I mean, we took the black hole masses as a given. So I'm probably the wrong person to ask that question.
Can you tell us how much larger are the black holes in BCGs compared to normal galaxies? Are they, so the galaxy bulge, black hole mass, well, but this doesn't include your work.
Well, the galaxies, some of the galaxies are here. I mean, actually, probably should be all of the galaxies here.
Oh, okay. So it's not much. Sort of
it's not much, yeah. Well, yeah, I mean, but well, wait, I can show you that plot actually. So if you look at the black hole mass barge mass, so the dashed line here is the best fit relation to the locus, or all galaxies actually. Okay, so most of them, or many of them are, should be here, should be 9, and then they are 9.5, a factor of 2, 3, something like that. Still a lot, if it's systematic.
All right, so there may be some process in clusters that
makes this addition.
Sort of 2 or 3 times bigger than.
Exactly. Yeah. That's the point. Yes.
Actually, not to be tedious, but just looking at your plot, I think that the worst relationship you have is this massive black hole versus bulge mass, right?
Yes.
And so that, in a way, means that the total mass drives both stellar formation and black hole formation. Those are the 2 fundamental correlations there. And this one is just happenstance.
I agree. I don't like this. I'm not a big fan of the black hole mass bulge mass relation. Yes, it's a terrible correlation.
I mean, to me, it's not surprising that a significant part of the mass in the center of the dominant galaxy has an external orb. It's not just from the galaxy itself. And have you subdivided the cluster sample into like cool core and non-cool core?
So
Cooling flows or mergers?
17 clusters and groups. That's nothing. Freddie is doing that. Yes, she's working on that. But I know if I can tell the result, we didn't see any difference between cool cores and non-cool cores. Preliminary, yes. Thank you, Lorenzo. Always helpful there in the back.
Our second speaker today is Tingting. She's a graduate student at the University of Maryland, and she's going to graduate this summer. And she's working with Professor Suzy Gerzari at the University of Maryland.
Okay. Can everyone hear me? Okay. Thank you very much, and thank you for the opportunity for me to tell you a little bit about my work. So let me just give you a quick review of this picture of the formation of supermassive black hole binaries. Observationally, there seems to be a supermassive black hole at the center of all galaxies, all big galaxies. And as galaxies merge in the lambda CDM universe, we would expect that supermassive black holes will also eventually come close together, first through dynamical friction and three-body scattering of stars. Then at closer separations, by exchanging angular momentum with a viscous gas disk, and at very close separations, gravitational wave radiation drives the, thank you very much, drives the orbital decay of the binary. So a lot of theoretical work has been exploring the observational signatures of supermassive black hole binaries at this very last stage. So in those simulations, they find that the binary torque clears out a low gas density cavity, which has a radius about twice the orbital separation, and mass is created through a pair of accretion streams onto the binary, which feed the mini disks around the black holes. They also find that as a result of this accretion pattern, the mass accretion rate onto the binary is strongly modulated, as you can see here, on a time scale that is about the binary orbital period. So for supermassive black holes of masses 10 to the 6 to the 9 solar masses, this time scale is about a few months to a few years. And more recently, Dan D'Orazio, who's now at CFA, and his colleagues proposed a Doppler boosting model. And in this system, it's viewed at a high inclination angle, and the emission from the secondary, but the mini disk of the secondary gets Doppler boosted as it travels along this along the line of sight at a relative speed. So that modulate the causes the modulation in the apparent flux, which has been fitted quite well to the light curve of the binary candidate PG1302, which was discovered in the Catalina real-time transient survey. So motivated by these theoretical predictions, there have been a couple of systematic searches for periodic quasars in large time domain surveys. So I've mentioned the search in CRTS, and people have also looked in the PTF data, and we did our search in the Pan-STARRS 1 median deep survey. So I think many folks here are quite familiar with the Pan-STARRS survey, but just as a very quick introduction, the median deep survey focuses on 10 circular fields distributed across the sky. Each field is about 10 square degrees in size, and their locations are chosen to overlap with existing extragalactic survey fields. So we started with about 300,000 point sources in the median deep survey. We cross-matched them with a catalog of deep stacks in the PS1, GIZ, and the CFHT-U bands. We select quasars by their color, U minus GG minus R color. We select the variable ones by comparing their observed variability with stars of similar brightness. We use the lump scalar parallelogram to look for a coherent signal across in at least 3 filters. We require a minimum signal noise and at least 1.5 cycles of variation. So at the end of the search, we identified 26 candidates in the 10 ND fields. We then follow them up with spectroscopy. For those that do not have archival SDSS spectrum, we follow them up with the Gemini and the Discovery Channel Telescope. We can measure redshift of the system, and we are seeing that we are actually more sensitive at high redshifts, which is to the contrary of what we expect for a decrease after redshift 1, which is expected for a flux limit survey like Pan-STARRS. We can also measure black hole mass of these systems, and we see that most of them have masses between 8 to 10 solar masses. So here I'm showing all the candidates in the Pan-STARRS GIZ bands, and as you may see, so I plotted these sinusoids to guide the eye, and you may see that most of them had 2 or 3 cycles. And if you look at the candidates from Graham et al. And Carisi et al., and here I'm just showing a few examples, they are also finding these short periods candidates that have 2 or 3 cycles over the baseline of the survey. But here's the problem. When we're looking for a periodic signal on a time scale of a few years, when total baseline of the survey is only also a few years long, we have to be careful that red noise can easily mimic periodicity over a small number of cycles. So in this example by Vaughan et al., so the top panel is showing, so the black points are the light curve of PG1302, and it's been fitted to a sinusoid. And what they did is that they took 2 different red noise models, the so-called damped random walk and a broken power model, and they simulate light curves, which is indicated in pink. And then they downsample the light curve to the observed cadence of the survey and added photometric noise, and they show that they can be fitted to sinusoid just as well over 2 cycles. So to put our candidates to the test, we use a combination of archival data and new imaging data. So Pan-STARRS operated for about 4 years, and we were able to extend the baseline back using the Stripe 82 archival light curves. And if we also been monitoring these candidates with DCT and more recently the LCO network telescopes. And here on the left, I'm showing you a few examples of candidates that have extended data. And so, again, the sinusoids are to guide the eye. And you can see that some of them look kind of persistent over 4, 6 cycles, but some of them do not look persistent at all. And this is just a histogram to show you that before, on the PS-only baseline, most of the candidates only have 2 or 3 cycles, but we are able to extend to 4, 5 cycles, and sometimes even more. So, and now, next we have also considered the red noise in the light curves. And here we model the signal term using two different models, the DRW model and the broken power law. And here we adopt a low frequency slope of -1 and a high frequency slope of -3. And for all candidates on the PS-only baseline and extended baseline, we want to ask whether the light curve can be characterized just by damp random walk or broken power law, or do we actually need extra periodic components? To do that, we compare our candidates with simulated light curves. So the simulations are shown in the dashed histogram. And we choose a significance cut such that about 0.3% of the simulations would pass our selection as false positives. We then apply the same cut to our real candidates, and we selected 3. So in other words, these candidates have a preferred periodic component in both their PS-only light curve and the extended light curve. We then simulate light curves on the broken power law model. We pick our 3 sigma cut, but this time none of the candidates look significant. So now we look at these 3 candidates and see if there's a preferred mass ratio that we can infer from this sample. So showing on the left is the predicted distribution of resonance times, which is dependent on the black hole mass ratio, and the orbital period. So the dashed line shows the expected distribution, assuming the binary is purely gravitational wave driven, and we take into account the fact that the Pan-STAR surveys was only about 4 years long, and there's a limited window of binary resonance times that we can probe. So as you can see that the distribution of the full sample of 26 candidates is poorly matched to the expected distribution, even for an extreme mass ratio like 0.01. But for the down-selected sample, we show that it's a much better match if we assume a mass ratio of 0.3, which is quite reasonable. We can also measure rate of these binaries. So out to redshift 2, so these 3 candidates were selected in a sky area about 50 square degrees. So at out to redshift 2, that's about 0.06 per square degrees. Or out to redshift 1 is about 0.02, which is compatible with the upper limit predicted by Voluntary et al. In terms of the number of binaries per 1,000 quasars, we're seeing something like 0.3 out to redshift 2 and 0.1 out to redshift 1 or 1.5. So that's a factor of field lower than the rate implied by Graham et al. And Chris et al. So there's a disagreement there, but I think that's not a big surprise. Because in about a year ago, Susanna et al. Took these binaries, selected a claim by Graham et al. And Chris et al., and calculated a gravitational wave background amplitude from these binaries. And they take into account, they use different mass ratio models and take into account the uncertainty in the mass measurement. And let me just highlight these dashed lines, which can be a little hard to see. What they're saying is that if all these binaries are real with the parameters claimed by the authors, the predicted amplitude will be a factor of few higher than the current upper limit from the pulsar timing rays. So the current best limit is given by the Parkes pulsar timing array at 10 to the minus 15. This is nanogram 9-year, but now they just released their 11th year data. And here's the European pulsar timing array. So in the last few minutes I have, I'd like to talk about gravitational wave astronomy. So on this landscape of gravitational wave, different gravitational wave sources, at the high end of the observed gravitational wave frequencies, of course, LIGO, and at the very low end, at the 10 to the minus 9 to 10 to the minus 7 hertz frequencies, those are the frequency regime of the pulsar timing arrays, and the loudest expected sources in their frequency bands are the supermassive black hole binaries. And in the past few years, pulsar timing arrays have started to put some very interesting upper limits on the gravitational wave background. I also should probably mention that they can either detect the binaries as collectively to measure a gravitational wave stochastic background, so a symphony of these binaries, or if they're very loud nearby ones, they can detect them as individual sources. So this is their upper limit on some of the models of the stochastic backgrounds, and they're starting to rule out some of the more optimistic models and starting to eating into some other models. And if you look at the timeline, we are here somewhere between 10 and 15 years, and there's a very good chance that we can expect to detect the gravitational wave background in the next 10 years or so. In terms of individual or continuous wave sources, they expect that, so these blue dots are realizations of nearby sources, and they expect that the International Pulsar Timing Array, which is the combination of 3 PDA experiments, could reach enough sensitivity to detect some of the loudest nearby sources. So as observers, what can we do? So I've been telling you that these periodic variations could be an EM signature of supermassive black hole binaries in very close separations. So a search in the time domain can potentially find EM counterparts of these low-frequency gravitational wave sources. So here I'm showing, so these contours are the predicted first most likely individual sources that can be detected by the IPTA and the SKA, SKA1 and SKA2. And the dashed box is what LSST will be sensitive to. So, and we estimate that some 10,000 candidates, this box could be populated by some 10,000 candidates with more than 3 cycles, and many of them will have 10 cycles or more, so that should dispel any doubts about their periodicity. So, as a concluding remark, I would say the future of multi-messenger astrophysics with the pulsar timing arrays is very bright and very loud. So I'll just leave my conclusion here and take any questions. Thank you.
So a lot of quasars have been monitored in the radio for decades. And as far as I know, none of them have any observed periodicity. Is that just because these are so rare that those few hundred quasars that are monitored in the radio just aren't?
Yeah, I'm not aware of any systematic monitoring in the radio. There is, however, a candidate called 3C66b. It's a radio source. It's being ruled out by the pulsar timing array. So if it is it has the mass and the binary parameters claimed, PDA should see it already.
Well, there are a number of programs of long-term monitoring of radio quasars. And, certainly just to calibrate the DLA, for example, point sources are looked at every month for, ever since the late 70s.
Okay.
So I had a couple questions. What method you use to select the variable quasars? Because you showed like a curve near the beginning.
Right.
So I was wondering what those axes were. Yeah.
Yeah, so so the black crosses, it's crosses, it's a little hard to see. So we take we look at each quasar and take the stars in its neighborhood. So most stars are not variable. So these are their variability versus magnitude relations. So the stars should lie tightly along this relation, but anything above that are potentially variable. So we make a 2 sigma, so they have to be at least twice as variable as that. So that's the red dashed line.
What does the y-axis do?
So that's basically the standard deviation of the light curve.
RMS?
Yeah.
Okay. I would worry about like fainter quasars. I don't know if you impose some limit, but at fainter magnitude, RMS can be big even though, like, so maybe like a chi-squared calculation would be helpful there. And my second question was, so in your last slide, you showed the medium view field square versus the LSST prediction. So they're,
Right.
they look kind of similar. LSST doesn't improve on that by much. Is that the right way to interpret that?
Right. So you're saying this frequency doesn't improve that much. So we're assuming 3 cycles. The CRTS baseline about 9 years. LSS is 10 years, so that's not that much different. But LSST will be able to find a lot more of these. I think that's the takeaway.
Okay. Yes. Exactly. Yeah. I was going to say because it goes so much deeper, you would think.
Right.
Yeah. Okay. Thanks.
Any other questions? Upstairs? Not that stay taking it up.
To introduce all.